Hey guys, welcome back to another video. So in today's video, I'm going to be talking about electron configuration. So the electron configuration is basically this really long order that sort of tells you which electrons in an atom of an element corresponds to which orbital. And it's really long. It's really annoying sort of to memorize. So I thought it'd be cool to share with you a way I use just to sort of put it in the electron configuration order. So I mentioned something about orbitals. This is just going to be a really small sort of description of what orbitals are. But orbitals are sort of regions of probability. They're just regions of probability. So they aren't physical regions, but they're regions. Oh my god, that's probability. They're regions in which electrons inhibit this probability-wise 90% of the time. So it doesn't actually stay in that region. Electrons move around a lot, but it's sort of in the vicinity of the nucleus. So there are sort of four different shaped orbitals. And the way I like to picture it is in terms of the periodic table. So this sort of region, these two columns are the s orbital. This block is the transition metals are d orbitals. This orbital, this block here is the p orbital. This is actually also the s orbital. And this is the f orbital. The lanthanides and actin. These are the f orbitals. Now, we can essentially sort of use the periodic table and determine the electron configuration order. So let's do that. So let's say we have something called phosphorus, right? We have an atom of phosphorus. We want to know what the electron configuration of an atom of phosphorus is. So I'm going to do this step by step. So the s orbital can have a max of 2 electrons. The p orbital, 6 electrons. And the d orbital, 10. And lastly, the f orbital, equals 14. So back to phosphorus. Let's do this sort of pictorially. So phosphorus has 15 electrons. Let's start from the first electron. 1s1, 1s2. So 1s2. 1s2, 2s2, right? Because lithium and beryllium, the third and fourth electrons, 2s2. Then 2p6, all this is still filled. 3s2. 3p3, because 13, 14, 15. And a good way to check that this is actually an atom of phosphorus is there should be 15 electrons, so the small sort of superscripts should add up to 15. And they do, in fact. So this is the electron configuration for phosphorus, and we can do this for pretty much all the other elements. This order that we're filling it in is something called the Aufbau principle. Aufbau principle. The Aufbau principle tells us which electrons fill in which order. So they fill in this certain kind of order. But like everything in chemistry, there are always exceptions. So let's talk about some of those exceptions. I'm going to erase some of this. Actually, I'm going to erase this. Okay. So some of the exceptions are copper and chromium. So let's look at copper, for instance. If we follow the same order that we talked about, it should be argon, this is sort of a shorthand way of writing it. I'll mention a little bit more about that later. So it should be 4s2 3d9. That's what we expect to happen based on what we've been talking about so far. But when we actually look at this experimentally, this is not the case at all. Actually, the correct configuration is 4s1 3d10. Now, the reason for this is because electrons in general, or orbitals in general, like to be half filled. The reason for this is half filled means less minimize repulsions. So the lower the repulsions, or the less likely the repulsions, the more stable the atom is. So S normally has 2 electrons, but in this case it has 1, and because it's half filled, it minimizes repulsions and it's more stable this way. Now we can do this on chromium as well, because this was copper. Chromium is something very similar. It likes to be half filled. Let's look at chromium. So chromium, we expect it to be argon 4s2 3d4. As we know, this is completely false. The actual configuration is this: argon 4s1 3d5. Notice both the d orbital, which has 10 electrons normally, has 5 electrons, so it's half filled, and the same thing with the s orbital. So these are 2 exceptions to the Aufbau principle, and this is something you should sort of know, because exams like to trick you, and they ask, okay, what's the configuration of this, and then if you answer it how it should be, that's actually wrong. On a final note, I'm now going to talk about sort of the shorthand method that I just used. It's called noble gas configuration. So what noble gas configuration does is, let's say I want to find calcium, right? The electron configuration for calcium. Then I don't want to write all this, right? So I'm just going to say argon 4s2. So what this does is, this is sort of a placeholder for all this, like 1s2, 2s2, 2p6, 3s2, 3p6. So instead of saying all that, I'm just gonna use this as a placeholder. This works for all the noble gas sort of configurations. It can be used for pretty much all the elements. And I'm gonna end this episode with some sort of electron configurations and how they relate to ions. This is also quite unconventional, so this could be used as a trick in some exams. So this is the order in which electrons like to get ionized. So if you look at Mn, let's say Mn2+, right? So it's right here, 25 electrons. You expect it, right, to be argon 4s2 3d3, right? So normally it would be 3d5, but because it lost these 2 electrons, it should be 3d3. But again, this is wrong, because this is just something you should know. Electrons like to get ionized in this order. So if you see here, this sort of row in manganese, it has s orbital electrons that it would like to lose first. So it doesn't have a p orbital to lose in this level, but it has s electrons that I'd like to lose. So instead of this, it would actually be this, argon 3d5. So all the 4s2 electrons are lost. This is another trick exams would use, so I think you guys should just sort of take note of this. Alright guys, that's the end of this video. See you next week.